In mathematics, a function space is a set of functions between two fixed sets. Often, the domain and/or codomain will have additional structure which is inherited by the function space. For example, the set of functions from any set X into a vector space have a natural vector space structure given by pointwise addition and scalar multiplication. In other scenarios, the function space might inherit a topological or metric structure, hence the name function space. In linear algebra, let V be a vector space over a field F and let X be any set. The functions xv can be given the structure of a vector space over F where the operations are defined pointwise, that is, for any f, g, xv, any x in X, and any c in F. Define f plus g x equals f x plus g x c f x equals c f x. Display style begin aligned f plus g x and equals f x plus g x backslash c dot f x and equals c dot f x. End aligned. When the domain X has additional structure, one might consider instead the subset or subspace of all such functions which respect that structure. For example, if X is also vector space over F, the set of linear maps xv form a vector space over F with pointwise operations, often denoted hom. xv. One such space is the dual space of V. The set of linear functionals Vf with addition and scalar multiplication defined pointwise. Examples. Function spaces appear in various areas of mathematics. In set theory, the set of functions from x to y may be denoted x via yx. As a special case, the power set of a set X may be identified with a set of all functions from x to 0, 1, denoted 2x. The set of bijections from x to y is denoted x left right arrow y. The factorial notation x may be used for permutations of a single set X. In functional analysis the same is seen for continuous linear transformations, including topologies on the vector spaces in the above, and many of the major examples of function spaces carrying a topology. The best-known examples include Hilbert spaces and Banach spaces. In functional analysis the set of all functions from the natural numbers to some set X is called a sequence space. It consists of the set of all possible sequences of elements of X. In topology, one may attempt to put a topology on the space of continuous functions from a topological space X to another one Y, with utility depending on the nature of the spaces. A commonly used example is the compact open topology, e.g. loop space. Also available is the product topology on the space of set theoretic functions, i.e. not necessarily continuous functions, yx. In this context, this topology is also referred to as the topology of pointwise convergence. In algebraic topology, the study of homotopy theory is essentially that of discrete invariants of function spaces. In the theory of stochastic processes, the basic technical problem is how to construct a probability measure on a function space of paths of the process, functions of time. In category theory the function space is called an exponential object, a map object. It appears in one way as the representation canonical bifunctor, but as single functor of type x dash, it appears as an adjoint functor to a functor of type times x on objects. In functional programming and lambda calculus, function types are used to express the idea of higher order functions. In domain theory, The basic idea is to find constructions from partial orders that can model lambda calculus by creating a well-behaved Cartesian closed category. In the representation theory of finite groups, given two finite-dimensional representations V and W of a group G, one can form a representation of G over the vector space of linear maps Hom V, W, called the Hom representation. Functional analysis. Functional analysis is organized around adequate techniques to bring function spaces as topological vector spaces within reach of the ideas that would apply to normed spaces of finite dimension. Schwartz space of smooth functions of rapid decrease and its dual tempered distributions. LP space. C. R. Continuous functions endowed with a uniform norm topology. CC. R. Continuous functions with compact support. B. R. Bounded functions. CO. R. Continuous functions which vanish at infinity. CR. R. Continuous functions that have continuous first-order derivatives. C infinity. R. Smooth functions. C infinity. C. R. Smooth functions with compact support. D. R. Compact support in limit topology. Weak P-Sobolev space. OU holomorphic functions. Linear functions. Piecewise linear functions. Continuous functions. Compact open topology. All functions. Space of pointwise convergence. Hardy space. Holder space. Cadillac functions. Also known as the Skorokhod space. Norm. If Y is an element of the function space C A B, display style mathcal C A B, closing curly bracket, of all continuous functions that are defined on a closed interval A B, the norm Y infinity, display style Y underscore and D, defined on C A B, display style mathcal C A B, closing curly bracket, is the maximum absolute value of Y x for A x b Y max A x b pipe Y x pipe, where Y element of C A B, display style Y equivalent max underscore A leq x leq b Y x q quad text where Y in mathcal C A B backslash comma dot closing curly bracket. Bibliography. Kolmogorov A N and Foman S V 1967. Elements of the Theory of Functions and Functional Analysis. Courier Dover Publications. Stein, Elias, Shikachi, R. 2011. Functional Analysis. An Introduction to Further Topics in Analysis. Princeton University Press. See also, List of mathematical functions. Clifford algebra. Tensor field. Spectral theory. Functional determinant. Footnotes